what am I going to talk about today? I want to talk about web UIs, which is itself sort of weird, because I work at Jane Street. We are a trading firm. We are not a web company. Our business is not presenting web user interfaces to third parties. So why do we care about this? Well, we care about it because we need to build user interfaces for ourselves. We're a prop trading firm, which means our business is running our own trading strategies on the world's electronic exchanges. And that is an intensely technological affair and an intensely data-driven affair. And that means we need user interfaces that reflect that, and that in particular are good at dynamically transforming and interacting with complex data sets. And that's the kind of problem that is going to drive what I want to show you. And I'm going to talk about some techniques to make it easier and better to build these kind of applications. But before I go into the how, I want to talk a little bit more about the why. And in particular, let me bring up, it's really small font size, what looks like the world's most boring user interface. It's a table. So I want to actually highlight that it's actually not quite as boring as it seems. First of all, it's like kind of interactive, so I can like click on things, navigate around, I can edit stuff, and that updates the data. I can search for things, and this actually is a filter, so if I do this, actually dynamically narrows down the view to a subset of the data. I can decide, oh, there's some of these dynamic values here, but I want to sort on one of them. So now it's sorting on these values as they're dynamically changing, which means in some cases you'll see the rows move up and down over time. And I guess another point we're saying is there's a lot of data, so like really a lot of data, like there's like 100,000 rows in here. And it all renders pretty zippily in that context. And the data is changing. It's maybe not obvious how much it's changing, but if I sort by this field and put this now is sorted by most recent time of update. So like there's a lot of stuff going on here, and even so it's all still kind of zippy. So why is that? Well, there's a lot of algorithmic stuff going on, work that's being done to make this perform well, and to get a sense of what's going on. Oh, that's a terribly small font. A sense of what's going on here, it's useful to kind of look at the inspector to see what's actually happening. So here, let's open up and look at the actual table itself. Okay, so here are the rows. So you can sort of see these are the rows that show up in the table. And I said there were like 100,000, but that doesn't look like 100,000. But actually what happens when I scroll, you'll see like some rows are being added to the bottom and taken off the top. And then actually, if you look at the very top, there's this height field. So basically what's going on is the UI is detecting where we're scrolled to, and it understands the height, the proposed height of all the elements, and where they are all located in space, and picks out the set of things it needs to render, and knows the size of the things it's not rendering, so it can like fold that together and compute the height and just stick that there, all for the purpose of minimizing the amount of stuff you throw at the DOM, right? The DOM itself is this tree-like imperative API in which you express to the browser what is it that you would like it to show to the user. And so like filtering, sorting, transforming, interacting, there's like a lot of stuff going on and a lot of optimization going on, and that's all kind of complicated to do. Like I don't know how many of you have tried to build a like highly data-intense reactive UI like this, but you can do it in a kind of straight-ahead way, but it's like slamming your head into a wall to do it, because what you need to do is a kind of detailed incrementalization of the program that you're building. Because UIs in general are kind of an incremental programming problem, which is the thing we'll talk about more in a second, and doing that by hand really sucks. Like it's an unpleasant programming idiom, it's hard to get right. I like this a nice analogy, which if you ever heard of dead reckoning. Dead reckoning is a way of navigating. What is dead reckoning? It's where when you're going around, you keep track of how fast you're going and what direction you're going, and you add it up, you integrate, you sum together all the little moves to figure out where you are. And the reason dead reckoning is terrible, like you do it when you need to, but it's the worst kind of navigation because the errors build up. It's easy to make mistakes along the way, and you sort of don't know where you are on the map. And what I want to talk about is a programming idiom that lets you program in this way, that's both highly efficient and lets you understand where you are in that map and talk in natural map coordinates rather than talking about the sum of a bunch of tiny little changes. So that's kind of the goal. before I get to the techniques I want to talk about, well, I guess one other thing I should say. So Jane Street is also weird in a number of ways. One of them is we use OCaml as our primary language for everything, including web UIs. So all of this whole talk is going to be about libraries that are implemented in OCaml, and I'm going to throw up some code on the board in OCaml. I'll try to explain it. You're not expected to understand how to peer through the syntax, but it's kind of there to help you navigate what's going on. I do think the ideas here are transportable. You should be able to take these and apply them in other languages and other contexts. So with that said, before I go into the techniques, I want to say something about how to approach this problem, the problem of expressing a UI nicely, before we talk about the optimization bit. And so the whole talk, in some sense, hangs upon an unsupported assertion, which is the topic of this slide, which is that the thing I'm about to show you is a nice way of expressing UIs. Happily, this is not novel. This is not something we've come up with. This is really just a rip-off of some mix of Elm and React and other similar kind of techniques. So I'm just going to kind of briefly explain our kind of spin on this, which is not in an important way different from what you'll find in the Elm and React worlds. And if you don't believe it's a good idea, go talk to Evan Saplicki or Jordan Walk or someone like that. I'm not going to defend that here. But I am going to try and explain it. So the basic approach for how you model a UI, so it's going to be highly functional in style, and it's organized around 3 different types: the model, the virtual DOM, and the action type. So the virtual DOM is in some sense the simplest one to explain. The virtual DOM is an immutable data type that represents the DOM you wish you had, right? It's not this imperative tree of things. It's your own separate immutable data type that you use for representing what you would like to put into the DOM. And that is a shared data type that any UI that you're going to build with this approach is going to use. And then the other 2 types, model and action, are types that are specific to the particular application you're building. The model is essentially the data model that you have that determines what you want to show people. It doesn't have all the presentation details in it, but it has all the core information from which those presentation details can be derived. And then the action represents state transitions, updates to your model. And there's this kind of the arrows in the diagram represent the basic flow through which this application goes. So you start out with a model. You apply what we'll see is just a simple function from your model to produce the virtual DOM that you want to display. The virtual DOM contains within it callbacks to be registered with the DOM, which are essentially used to trigger actions. Those actions are then applied to the model to update it, and that, again, updates the virtual DOM. So that's the basic loop, and in that loop, the interactivity of the UI is found, right? So that's the kind of core representation there. And this here is what that looks like in OCaml. So here's a signature that you can fill out in order to be an app in this environment. You need to provide 2 types, the model and the action, and 2 functions. Apply action, which tells you how to update the model when an action occurs, and render, which takes the model and produces the virtual DOM. Okay, so I'm not going to, again, go into more details about exactly how this works, and really the heart of the rest of the talk is how to optimize these functions. And in particular, we're going to really focus on the render function, the one that goes from the model to the virtual DOM, and how to do that in an efficient and, as it turns out, incremental way. And so this gets to the heart of the thing I was saying before. You really want to think of your UI as an incremental computation. And what I mean when I say an incremental computation is one that is efficient not just at doing the entire end-to-end computation, but in refreshing that computation when the input to the computation changes in small ways. And this is unsurprisingly, when you think about it, at the heart of the user experience at many different UIs, because there's a lot of data that goes into the initial render that says all of the things that you need to show the user. But when things change, and UIs are all about dynamic interaction, when things change, they typically change in small ways. Not everything flips all at once. Small parts of the data model, small parts of the interaction state that says where you're focused and what you're pointing out, little bits change, and those little bits should be cheap to apply and freshen up the world with. And so the following, whoop, that's not helpful. So the following little picture kind of gives you a sense of what the basic computational pipeline is. You start with a model, you then compute the virtual DOM with a pure function from that model, and now, because this is, say, our first render, There's the DOM tree in the browser. It ain't right yet. It's whatever it is and not what we want it to be. So we have some function, this is now an imperative function, that takes the virtual DOM and slams the DOM itself to match your intent. So that's like step one. And then what happens when an action occurs and you get a new model prime, which is different from the original model? Well, you could do this, right, which maybe we can henceforth call the stupid thing, which is to just recapitulate the entire computation, recompute the virtual DOM from scratch, slam it into the DOM from scratch. So that's terrible. We don't want to do that. In fact, no one who uses virtual DOM does that. What they do instead is they take advantage of the fact that the change is small. So this is an incremental computing trick. And just as a note to you guys who might be looking at some UI framework somewhere, buried, usually somewhere inside the documentation, where they don't want to show it to you because it's a little ugly, buried in every user interface toolkit is an incremental programming system. Sometimes not very good, sometimes well thought out, but like it's in there somewhere and you should understand how it works when you're thinking about which system you want to work in. So for these virtual DOM-based systems, a standard trick is to take advantage of the fact that the model probably changed only a little bit, so the virtual DOM probably changed only a little bit, so the DOM should probably only have to change a little bit. So we compute a diff. Right? A diff between the virtual DOM and the previous virtual DOM and the new virtual DOM. And that diff is essentially a set of instructions that tells you how to update the old virtual DOM to get the new virtual DOM, or, transposed slightly, how to update the DOM to get the DOM that we want to have. So there's a kind of parallel transport of this little arrow over to apply that, so it's logically that same little arrow to the DOM. So, nothing new here, totally standard trick. That's not the portion of the diagram I really want to talk about. I really want to talk about this orange arrow. And the orange arrow, like I want to do the same thing on the model side. For a small UI, you can kind of get away with just using the virtual DOM because that minimizes this most expensive thing, which is like talking to the browser render engine and making it do things. But the recomputation of the entire virtual DOM is not so hot if the virtual DOM is big, if the model is big or the virtual DOM is big. Well, that's not going to work so well. And so you want some way of optimizing both of these arrows. And the arrow on the left is harder. Right? The arrow on the right is optimizing a computation on a single standard data type, doing a single thing. Whereas on the left-hand side, well, the model is actually a totally custom, chosen by the user data structure. And so how we take advantage of the similarity between the old model and the new model is not nearly so clear, and the incrementalization stories are uglier when we talk about that part. And so the focus of this talk is going to be about trying to understand a different kind of approach for getting this incrementalization done. So what we're specifically going to do is we're going to achieve our incrementality at first with a library called Incremental. So this is a library that we've developed at Jane Street. We've had it for a long time. It was actually developed not for this application. It was developed for all sorts of different systems that we were building, and we only later thought, oh, we could like compile this and run it in the browser because we have a JavaScript backend. And so the very same library has done a lot of different purposes on a bunch of different platforms. The basic idea of incremental is you basically capture a trace of your computation in the form of a dependency graph that gets built up as your computation unfolds. And then when you rerun the computation as some of your inputs change, you use this trace to compare what you need to do now with what you did last time. And that allows you to just refire subsets of the computation rather than having to redo everything. If you use Excel, the Excel model is a little bit like this. You have a bunch of cells. Each one of them has equations. The equations can refer to other cells. If you've used Excel much, you have a big, complicated sheet. You modify just like some piece of it. It doesn't have to freshen it up by recomputing everything. It essentially computes the transitive closure of the parts that have been dirtied, the parts that have been changed, and just refires those. And that, at the heart of it, is the kind of core optimization that Incremental is built around. And this is actually based on yet older work. Takar at CMU did for his dissertation work on what's called self-adjusting computations. And Incremental is more or less an implementation of self-adjusting computations inside of the OCaml framework. So I want to explain the core of this API. I could explain it by saying, oh, it's a monad, but that's like a really lame explanation. So instead what I'm going to do is walk through the core combinators one by one and try and give you a sense of what they're useful for, and in particular what they do at the level of the graph. So The first one is map. Here is the type signature of map. So again, obscure syntax you don't know. Let me walk you through it. So here you take an A incremental, which is to say an incremental that computes a value of some unknown type A, and a function from A's to B's, and it gives you a B incremental. So this is take an incremental, apply a transformer, give me a new incremental. So how do we use this? Well, imagine we have an application where there's a base model, and we want, at the end of the day, to render two components on the screen at the same time, each of which derives from a different submodel. There's like two submodels and two subcomponents that are going to come out of this, and then we want to stick that together on the same page. So we can apply map twice to build the two subcomponents, incrementals representing the two subcomponents, by essentially projecting out the part of the model that we care about for this case. And we can then use map again to take the model, which again is just like this pure data representation, and do whatever transformation is required to convert it into the necessary virtual DOM. And now we're stuck because map can fan out, but it can't fan in. So we need to add another combinator. This one is called map2. And as the name suggests, it takes two incrementals, an A incremental and a B incremental, and a function that takes an A and a B and returns a C, and gives you back a C incremental. So it's a way of merging two things together, and we're going to, in this case, use this to merge together the two different virtual DOMs with a function that basically just takes the two trees and like slaps them together in some little, HTML-ish environment in which they're both going to reside. And now you have what looks more or less like a complete graph representing the computation for building a page. And of course, why do we want a graph? We want a graph for its optimization property. So let's talk about what happens when we make a change. So if we update the model, what happens? Well, every node, when it changes, when it fires, which it will fire when you just manually directly apply a change to it, when it fires, you see either did that modification actually change it, or is it equal to the old value? If it's equal to the old value, it cuts off, the computation ends there. If it's different, it propagates to all its children. So we're going to wake up sub 1 and sub 2. They're going to redo the projections out from the model. And let's say just sub 2 changed. Sub 1 is exactly as it was before. So that means the sub 1 incremental is now going to cut off. It's not going to fire again. But sub 2 will continue, and it's going to fire through the rest of the graph. And there you go. We have some incrementality. We have two components sitting side by side inside the same application. But when the data for one of them changes, we don't have to fire the other computation. Right? So some incrementality achieved. Okay? So those are our first two operators. The next operator is called bind. And with bind, we're going to solve a slightly different problem. Here, again, we have two components, and we're going to build up those components in the same way using map. But now, we're going to want to have a page which shows one or the other, depending on which mode we're in, which is like a totally standard thing. You have some UI that has multiple different views you can flip between. So we're going to use a bind node for that. Let's look at the signature of bind. It is surprisingly similar to map. You take an A incremental and then a function that takes an A and returns not a B, as with map, but instead a B incremental. And then the whole thing gives you back a B incremental. So the idea here is the function, instead of just taking a value and producing a simple value, it can take a value and return an incremental computation. In fact, it could select from multiple different ones that already exist, and that's what we're going to do here. So here we add the thing that takes the VDOM and it binds on the model, and then let's say it decides, based on what the current state of the model, that it's going to pull in the data from VDOM1 and put that on the page. So it does so. So now, if there are changes to the model that affect component 2, well, that part of the graph is quiesced. It's not going to run anymore, so we don't have to pay for that firing at all. And if there are changes that affect component 1, then they're going to flow through. And then if the model changes, such that it now wants to show 2 instead of 1, we're going to cut the connection from 1 and add a connection to do, and now the firing structure is reversed. Now changes to 2 will propagate, and changes to 1 will be cut off and dropped on the floor. Okay, so this gives us a very straightforward notion of dynamism in the graph. So the map stuff gave us static graphs, the bind gave us dynamic graphs. In fact, let's stop for a moment and think a little bit about what we have done so far in the talk. As I said, map has given us the static structure. And bind gives us a form of dynamism, but the form of dynamism is in some ways somewhat limited. So the form we saw on the previous slide was just selecting among multiple pre-existing things. That's not the only thing you can do. You could also allocate whole new computations inside of a bind node. That turns out to be useful. But that form of dynamism is somewhat limited in itself and is not easy to use in a highly incremental way, which is when you allocate new computations on the right-hand side of a bind, well, you're allocating whole new computations. You're not getting to reuse anything from the past. So you have dynamism, but the incrementality of that is compromised. And if you just step back for a second and see what have we gotten out of this model, if you're familiar with things like Elm and React, we've gotten more or less the things that those systems give us, which is you can take your thing, you can break it up into components, you can kind of control which components are shown, you can restrict the changes such that changes to one component don't force the renders of different components. And that's kind of that. Here's what it doesn't tell you a good way of doing. How about incrementally sorting 10,000 things? Like, it's just not clear how you can like break things into components and cut off stuff and thereby sort a big set of things, right? So there's a limit to the kinds of transformations we can effectively do. And that's, in some sense, the heart of what I want to talk about is how can we build abstractions which let us build more dynamic, more interesting kinds of data transformations that are still incremental at their core. So here's another type signature. I hope you're not too sad about seeing type signatures yet. It gets worse when I start showing code. So this is a function we're calling Incremap, and now I have to take a moment to apologize for a general functional programming nomenclature car crash, which is map and map. So there's at least two, arguably more meanings of map on the page. One, the capital map, map.t, is a finite map. It's a mapping from keys to values in like a concrete tree-like functional data structure. And then we're talking about mapping over an incremental value, and we're also going to talk about mapping over a map and mapping over an incremental map. So like this second kind of map is all about transforming the thing inside of a container. And incrementals are kind of containers, or maps are kind of containers. And so like, anyway, I apologize for how much it sounds like I'm stuttering and saying map, 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 map. Just, I'll try and be clear where I can about what the meaning of these things are. So what are we doing here? We have the input of the function is a map incremental. So it's an incremental node that just contains a data structure that is a map. That contains key value pairs, the type is k, the value is of type v1. And then we have a function from type v1 to v2, and the output we want is another incremental map, except now the data has been transformed, the data type is v2 instead of v1, and it's basically the obvious result you should get by transforming all of the data. And this is actually, like, writing a function that meets this signature is easy. Here is a function that meets this signature. So there's a little bit of syntactic nonsense here. This let%map is basically syntactic sugar for nicely using the incremental level map function. So roughly you can think about what's going on here is we're saying everything after the now highlighted line will be rerun every time m changes, every time the input map changes, and you'll get the map in its current state to look at and compute on. So the graph structure we get is something like this. There's the map we start with, is m prime we're computing, and it has the following lovely incremental structure, which is every time you change m, you recompute m prime from the beginning. So this does not, in fact, do us any good. We have met the type, but we have not met the desired performance characteristics, right? We've used incremental in a totally trivial way. And it's not obvious what we can do just given the combinators we have at our disposal to do something better than this, right? This is, I don't know what like static set of things I can do to map out different parts of the map and project them into different little incrementals like that. It just does not seem like a productive way to go. And what we're going to do in the end is we're going to take advantage of diffability, right? The fact that functional data structures often admit efficient diffing algorithms. So this is the signature of the Symmetric Diff function from our standard library, which we had pre-existing all of this web browser UI nonsense because it was a natural thing to want for other reasons. And Symmetric Diff takes as an argument two different maps with the same types for keys and values, and an equality function for comparing the data. And it returns to you a sequence of results, which are keys annotated by what happened between the first map and the second map. And left says there was a key in the second map, but not in the first. Right says it was in, left says it was in the first, but not the second. Right says it was in the second, but not the first. And unequal says it was in both, but with different values. So this roughly corresponds to add, delete, and change, right? And this operation is super quick. In particular, if the two maps you're applying them to, the second map is one that was derived by doing some set of efficient operations from the first map, then for various reasons having to do with how persistent data structures work, in order to do that transformation efficiently, really, most of the physical memory is shared between the two maps. You just had to update the spine a few times to add new entries. So the symmetric diff algorithm takes advantage of the fact that if two subtrees are physically the same pointer, you know that everything underneath them is exactly the same. So you can short-circuit the computation of the diff, which means that, roughly speaking, the cost of computing the diff is asymptotically the same as the cost of having made the changes in the first place. So this runs fast. You don't have to walk over your entire data structure to do this operation. So now we want to take this idea and embed it inside of the incremental context. And as we'll see, one of the nice things incremental does is even when you're not doing all of your work as part of the incremental graph, it's a really useful coordinating mechanism to hook together lots of different computations. So we need a hook. And that hook is going to be a function called DiffMap. So the idea of DiffMap is it's a map that gives you access to the previous value of the computation that you run. So if you have an A incremental, it produces a B incremental along with a function, but it's not like the normal function of A maps to B. It has that too. It has A as an input and B as an output, but it has an extra input, which is an optionally provided previous version of the computation. So it's like, if you could use the thing you did last time to optimize your current computation, you should feel free to do so. And DiffMap itself is not a complicated thing to add. We don't have to look hard at this implementation to understand it. I mostly want to highlight that it's pretty short, and that basically what it does is some dirty tricks about capturing a little bit of mutable state inside of the closure that's used for the transformation, and that's what that mutable state is used for capturing the previous version of the computation. And then, and this slide you really are not supposed to understand, again, this is the whole implementation of the Incremap that we started with. So we call DiffMap on the original map. We have this function now that has the old version optionally and the map it's supposed to depend on. We pattern match on the map, on this old version. If there's nothing, there's no old version, which is true in the first run, well, we just do the all-at-once computation. That's fine. If we have the old input and the old output, then we compute the actual symmetric diff next. And then we fold over that diff and do different things depending on what case we're in. In the left case, which is a key that was in the left but not the right, so that's the deletion case, we just remove that corresponding key from the output. In the unequal or right case, there's a new thing we want to add, so we just do map.set. We add in that new binding, but we apply the function f to the data before stuffing it in. So we sort of take the diff on the left-hand side and transform it into a diff that can be applied to the right-hand side. Right? So far, so good? And what's nice about this is it's actually a very general purpose thing. We're not really, in an important way, specialized to maps. We're able to do this, oh no. We're able to do this because it's a diffable data structure, and lots of functional data structures are diffable. So this is a pretty general purpose trick. But there's more we want to do, right? We can't build that whole complicated UI I described with just this trick. Here's another very useful trick. So we call this imaginatively Incremap prime. And this is almost not different from the Incremap. Basically, the difference is the transformation function. Instead of being a simple all-at-once transformation from this form of the data to that form of the data, it itself is an incremental computation. So now what we're essentially doing is, instead of just doing a single transformation, we're setting up an incremental pipeline for each element in the data. And this kind of nested incrementality is often important in more complicated cases where you have complex nested data and you want to handle it incrementally at multiple levels. So we're not going to implement this with DiffMap. This is more complicated than that. And if you want to think about why it's more complicated, you just need to think about the graph structure that's necessary to do this thing. So here we have M on the left and M prime on the right. And this is more or less the necessary graph structure for the performance properties we want, which is we need to fan out to all of the different entries in the data, and then feed those entries into these incremental pipelines I was talking about, and then take the result, the E prime, the transformed entries, and merge them in back together. And if you think about the propagation structure, well, M gets modified, unless it gets modified with an add to a single, or rather an update to a single key, well, we want to fire through just that key, right? Just the part of the graph that corresponds to that key. And that violates the invariant I told you before. Remember I said we modify a thing, and if it changes, then all of its children get woken up. Well, and you sort of need that in the ordinary case, because how does the child know whether or not its computation has changed? So in this case, we have to be able to build a special purpose computation that in a data-specific way understands things about the nature of maps and how they change, and knows things about the specific transformation to be able to pick and choose which of its dependencies actually need to be refired. So if all we have are bind and map2, we are dead in the water. They are not expressive enough to build the graph that we need. So the thing you need to build the graph you need is a little ugly, unfortunately, which is to say, we kind of took a little piece of metal and knocked out some of the interface and exposed an expert API to Incremental to allow you to build these things that give you kind of lower level access to the graph structure. And that's not an interface you want everyone to program with, but happily, you can find useful primitives that you can build on top of that lower level interface that themselves are really nice and let you do all sorts of useful things. And two of those nice primitives we call split and join. These are for maps in particular. And, well, there you go. You see the type signature. What else do I have to? Well, OK. By staring long enough at the type signature, you can sort of get it, but it's better to talk it through. So the idea is split takes an incremental, which contains a map, and gives you an incremental that contains a map, but where the data part of the map itself contains an incremental computation. And the idea now is that changes to the input map that just update a key are routed directly to the inner incremental, and changes that add or remove keys that then need to change the spine of the map, those go to the outer incremental. Right? And this more or less corresponds to the fan-out phase of that graph we were talking about. You kind of break up into a bunch of little incrementals, and you can control the addition and removal of those, which you need to be able to do in this structure. And then join is, of course, just the reverse. Right? It's exactly the inverse of split, and it just has the reverse type for that reason. It just takes a 2-level incremental map and flattens it into a 1-level incremental map. And then, joyously, incremap prime is just written like this. We split, we incremap, we join. And that gives us this richer structure right there. And you can build incremap prime that way, and you can build a whole bunch of different operations in the same style. And I think this is kind of a thing that we notice over and over in this work is there are some core pieces that are hard, but you can build on top of them beautiful, easy-to-reuse abstractions that can be used over and over again in a way that's easy for people to understand. So, just to kind of gather what we've done here, we've extended incremental in a number of ways. We added DiffMap, which all it required is the stomach to stick a little mutable piece in a closure somewhere, and now we have a general-purpose trick that works on any diffable data structure. And then we built split and join on top of this expert interface. And in fact, we really have two modules here. There's Incremap, which contains split and join and a number of other map-specific operations. And another one we built was IncrSelect, which lets you do things like thinking about selecting ranges of things and dealing with things like focus computations, which are also useful to handle in this way. So we've now built a number of different useful abstractions on top of this same core system, and these kind of abstractions have helped us build the kind of complex APIs that we were talking about. So, what are things to remember from this talk? There's just a few key observations I want you to take away. One is, UI design is an optimization problem. It's an algorithms problem, and it is best handled when you think about it that way. And in fact, the real trick, the thing that gives you the most bang for the buck, is to think about it as a problem where you can separate out the sort of nasty, low-level, painful problem of building a highly efficient UI that does exactly what you want into two beautiful problems. One is the problem of specifying the UI you really meant in a clean, functional way, and the other is the problem of building efficient algorithms that make that possible. And it's a lovely thing when you can take an unpleasant problem and break it into two high-class, interesting problems. Like taking the right frame on this really helps you do that. Another thing I want to convince you of is self-adjusting computations, of which Incremental is an example, is a powerful optimization tool and a powerful kind of organizing tool. It helps you build a complex set of different views on your data that all keep in sync in a clean and easy to organize way. it's a thing that's been around forever, and people don't use nearly as often as they should. So I really want to recommend, think about where you can apply it. And there are various implementations around. OCaml has a very nice one, but there are others as well. But I think it's totally worth thinking about that as a tool you can add to your toolbox. And finally, a thing you'll notice is, throughout this talk, is diff and patch had a surprisingly large part in the overall story. They showed up over and over again. They show up in the virtual DOM. They show up in a number of different ways inside of the incremental DOM world. And actually, if you zoom out and think about the larger version of this, when you think about the server side of this problem and you think about how you serialize this data over the network, diff and patch over and over show up as a way of bridging computational worlds, of taking functional data structures and mapping them onto incremental computations, or network protocols, or imperative APIs like the DOM API. And this, I think, is a general purpose lesson that you can use in lots of different contexts. Diffing and patching works nicely in a functional context, and it's just a very useful way of coordinating. So, as I said, mostly this talk is meant to be about the ideas, but there's also concrete software. You can download this on your machine and build, the example application is just grabbed from the open source repo and built on my box. You don't have to use Jane Street's infrastructure to do this. So at a minimum, it's a thing you can go and look at and experiment with on your own. So that's all I've got. Thank you very much.